Hydrodynamics. After completing this module, you'll be able to describe the basics of hydrodynamics. You'll be able to describe some more properties of a fluid, describe the difference between solid and fluid mechanics, as in the way you actually measure and model solids or fluids, the differences between those. And you'll also be able to describe the role of energy in fluid flow and consider some of the constraints that exist within the system. Hydrodynamics is basically the study of fluid in motion. And Bernoulli was the first person to coin that term back in the 1600s in his description of the flow of water. Now, hydro means water and dynamics means motion. So when Bernoulli was studying the flow of water, he was studying the hydrodynamics, and he coined that term first. Hydrodynamics is more complex than hydrostatics. I've already introduced you to hydrostatics earlier in the module. For example, the pressure in PSI equals the mud weight or the density of the fluid in pounds per gallon times 0.052, which was a constant, times the true vertical depth in feet. That's pretty much a hydrostatic equation. Hydrodynamics is much more complex than that, because there's many other variables that are introduced than those that are actually used just in hydrostatics. And these variables are specifically, we've got velocity, we've got the direction of flow, and we've also got the viscosity of the fluid as well. Now, hydrodynamics provides a link between pressure, velocity, and geometry, or the size of pipes or channels through which flow is occurring. So we've got a link between pressure, velocity, and geometry. Now, what actually is flow? I just mentioned flow. What is it? Well, we can define flow as a measure of the rate at which a fluid is moving. It can be measured as volumetric flow, or it can actually be measured as mass flow. We use both terms, volumetric or mass flow, within our industry. Most of the time during this course, I'll be talking specifically about volumetric flow, unless I refer to it as mass flow. Places you might find mass flow are when you're actually flowing gases through pipework. You tend to talk about mass flow rather than volumetric flow. When you're actually looking at the spec sheets of an MWD tool, you'll see the maximum flow through that tool quite often will be referred to in mass flow units rather than volumetric flow. Now, fluid velocity is related to flow, and it can be described as the velocity of a fluid through an aperture the velocity of a fluid through an aperture of known size. Now, an aperture of known size in our industry could well be the inside of a, say, 5-inch drill pipe, which has a known ID of 4.276 inches. And you'd express the fluid velocity through that aperture in feet per minute or meters per minute. And it relates to flow in that the flow rate is a volume per unit time, and velocity is a displacement per unit time through a known volume conjugate. So that you know the volume that you're pumping something through, and you know the velocity of it, and the velocity is basically a displacement per unit time. Discharge, it's another way of referring to flow. It specifically refers to the volume of fluid flowing along a pipe or a channel per unit time. Now, that's what I've just defined flow as. Well, discharge is what you'll find referred to in any fluid dynamics manual, or if you're reading about hydrodynamics or any of these textbooks that you read, they will refer to discharge, and they'll interchange the word discharge with the word flow. So basically they mean the same thing. Now, in the oil field, as usual, we're slightly different. We would reserve the word flow for fluid flowing through a pipe, whereas discharge would be reserved for the output of a pump. The two terms are pretty much synonymous, and they mean the same thing, and they've got the same units. They've got the same symbol, so it's Q equals volume over time. So flow equals volume over time, discharge equals volume over time. And obviously the output of a pump, as it's pumping fluid into a pipe, is going to be the same in volume per unit time as the fluid flowing through the pipe is in volume per unit time. So discharge and flow are linked like that. And discharge can also be related to the fluid velocity and the cross-sectional area of a pipe by the following equation. Q equals velocity, which is V, times area, which is A. Now, Q equals VA. Velocity is a length unit divided by a time. and area is length times length, or length times breadth, if you like. So we've got length times length times length divided by time. If you've got length times length times length, you've got volume, as in length, breadth, and height of an object is a volume. So you've got volume over time. So volume over time equals velocity times area. That's how these equations are related. And it's useful to remember both these equations because they can help us to visualize what effects variations in pump output will have on fluid velocity in pipes of varying diameter. So if you vary the diameter of the pipe, you can use this equation. If you know the flow in gallons per minute, you can then work out the effect on the velocity of that fluid through a pipe if you know the cross-sectional area of the pipe. The continuity equation suggests that the inflow will equal the outflow in a system. So whatever you pump in will come out. So Q1 equals Q2, where Q equals VA, as I mentioned before. So flow equals velocity times area. The continuity equation links areas and velocities in this system. And that can be demonstrated here. We've got a cross-sectional area of this piece of pipe here of half a square meter, and the velocity of the fluid going through that is 1 meter per second. And so that's V1 times A1 on this side, and V1 times A1 from the continuity equation must equal V2 times A2. So if we want to find out what V2 is, it's unknown at the moment. We know A2 is 0.25 square meters. So basically it's half the cross-sectional area of the original pipe that we're pumping into. So what's V2? What's the velocity of the fluid in this part of the pipe here? Well, we've got 1 times 0.5 square meters. So we've got 1 meter per second times 0.5 square meters gives you 0.5 equals V2, which is on this side, times 0.25. V2 must equal 2 meters per second. So basically by halving, this is just showing you here, simply by halving the cross-sectional area of this pipe, you've doubled the velocity of the fluid going through it. Because it's got the same volume and being pumped in, but it's got half the area to go through, therefore it's got to go faster. It's kind of obvious. This just demonstrates that it gives you the maths behind it as well. So how do we actually model or even measure flow? Well, in solid mechanics it's pretty easy. We can measure the position of a body in space as a function of time. And if we actually know that, then we can derive the velocity, the acceleration, and also forces involved in the motion of this body. But when we're dealing with a fluid, or with fluids, we're not actually dealing with a fixed shape body as in this sphere that's moving back and forth. It's not a fixed shape body in space. We're actually dealing with what's known as a continuum. It's a continuous flow. It's like it has no defined, distinct shape. It's a flow past a point in space. Now, when we're actually performing measurements on a continuum, the difference between measurements on a solid body and the measurements on a continuum, like a fluid, difference is that the measurement point remains the same, but the fluid's constantly being replaced. So as you can see, you've got a fluid coming along here, and we're performing a measurement at this point. So what we're really doing is actually we're tracking the history of a point in space. So we're keeping a history of that point to there. And that point has been occupied by a whole number of particles as they flow by. So we're not measuring any particular particle in this fluid as it flows along there. We're measuring the continuum. We're measuring the history of this point as the continuum moves by. So it's a completely different way of measuring, and therefore a completely different way of modeling. We still end up looking at forces and accelerations and velocities and so on, but they're measured and modeled in a slightly different manner. And it's important to just bear that in mind before we go any further. The reason we refer to the fluid phase as a continuum is that when we're examining how fluids behave as they flow, or how objects within them behave, we can assume that the molecules of the fluid are so closely packed together that the spaces between them are actually insignificant when you compare them to the size of the objects that are held within them. And the objects that are held within them in our industry could be things like rock cuttings, or we could talk about the borehole wall, the pipework, or any obstacle. But generally, rock cuttings is one of the objects that we would be describing the forces on and the way the fluid behaves around them and the way they behave within the fluid. So when we're talking about the rock cuttings and how they are suspended or how they fall through that fluid, we're making the assumption that the spaces between the molecules of a fluid are totally insignificant in our measurements, and to a great extent they are insignificant, and that assumption is perfectly valid. Now, in a mud manual, you may actually hear the base fluid of a mud being referred to as the continuous phase. Now, what that means is, in a water-based mud, you've got water as your continuous phase, and in an invert emulsion or an oil-based mud, the oil is the continuous phase, and the water that is emulsified in that invert emulsion is actually it's dispersed throughout the oil. It is not. It's not a fluid as such. It's not the continuous phase. So the continuous phase is the fluid that everything else is suspended within. Taking that one step further, the fluid can actually be thought of as a homogeneous or homogeneous isotropic continuum. Now, what I mean by that is it's homogeneous. It basically means it's the same. The consistency is the same all throughout the fluid. So if we look at the sphere of fluid, the actual consistency of it here is the same as the consistency of it in the center and at the other side. It may have clay particles suspended in it. It may be just a drop of water. But the entire thing can be thought of as being the same consistency throughout. Isotropic basically means that if you apply a load here, it will distribute the pressure that you're applying here throughout in all directions equally within it. Whereas most solids are anisotropic, in that if you applied a load here, it would bulge out more in one direction than it does in the other. So fluids are isotropic, they're homogeneous, and they're also a continuum. Now, moving on from that, let's look at the conservation of energy. Now, energy is the link between pressure and velocity in pipe flow. Now, energy is previously defined as the capacity to do useful work. We've already said that earlier on in this course. It's the capacity to do useful work, and it is a link between pressure and velocity. Now, fluids can actually store energy in three ways: pressure energy, kinetic energy, and potential energy stored in a fluid. Pressure energy, this is available when a fluid is under pressure. Now, pressure is a measure of the energy available to do useful work. The pressure energy equals the pressure divided by the density, fluid density, and also divided by a gravitational constant. Now, that's actually a very familiar equation, as you know. It's very similar to the hydrostatic pressure, or the pressure head equation, which I showed you earlier, which is pressure equals rho GH. Now, we've got pressure, and we've got rho G, and we've got energy. And as I mentioned before, sometimes in fluid dynamics, energy would be expressed in length units. So if we rearrange this equation, we could express the pressure energy of this fluid in length units, if you like. So it's exactly the same equation as the PSI equals density in pounds per gallon times 0.052, which is your gravitational constant, times your true vertical depth. In this case, your pressure energy, or the energy, could also be expressed in length units, relating it to TVD, and the pressure that the fluid is under due to the column of fluid above it, basically, the height of fluid above it. Now, the next type of energy that we have in a fluid is kinetic energy. Now, when it's actually flowing, it has energy because of its motion, and that's called kinetic energy, or sometimes called velocity energy in some texts that you might read. And the faster the motion, the greater the kinetic energy. Now, kinetic energy equals v squared, which is velocity squared, divided by 2g, 2 times the gravitational constant. And kinetic energy is also measured in units of length, and sometimes referred to as the velocity head. So you've got a pressure head and a velocity head, and you can express those in length units if you particularly want to. Now, potential energy. Now, this is basically the energy related to the location of the fluid, specifically its vertical location. In the case of a tank full of water, as I mentioned before, if you place it on the ground, there's very little useful work it can do because it's sitting there already. It's at ground level. And if you actually raise that up, if you place it on top of a building, then there's a lot of useful work it can do. There's a lot of energy that it can impart. It can use a lot of energy getting down to ground level as it goes through shower heads and taps and so on, or faucets in people's flats and things like that. Potential energy can be measured in units of length, and it's determined by the height of the fluid above some fixed datum point. Usually you would put it above mean sea level or something like that, or ground level. But it's above a fixed datum, and it's expressed in length units again. So just describe three types of energy, and they're actually related by what's known as Bernoulli's equation, Bernoulli's energy equation, in which the total energy equals the pressure energy plus kinetic energy plus potential energy. So we've got P over rho g plus V squared over 2g plus Z, or Z. Now, this equation completely describes the energy within a fluid. Now, applying energy, two aspects of energy can be useful when dealing with hydraulics. And the first aspect is that energy can be changed from one form to another, such as like potential energy can be changed to pressure energy and also to kinetic energy, as in when it starts moving. So if you raise this water and put it in a tank on top of a building, as it starts moving, it has kinetic energy. If you fill up the pipe all the way down to the bottom of the building and close your faucet or your tap or your shower head, you turn your shower off, there is a pressure behind that. The fluid has now got stored pressure energy in it, and it's wanting to use it. When you when you switch your shower on, the fluid comes through. It's the pressure energy that it had stored in it, sitting in your shower head, is now being released as it comes out, and it's being changed into kinetic energy. Now, the total energy is the same at different points in the system, even although the components of energy might be different. However, having said that, that's your conservation of energy. It becomes actually further complicated when we actually start to talk about fluids traveling over long distances, like pipes and annuli, because energy can also be translated into heat due to friction. So we have to change that energy equation a little bit. So we've got P1 over rho g plus V1 squared over 2g plus Z1 equals P2 over rho g plus V2 squared over 2g plus Z2 plus HF. And HF is actually described as the energy loss due to friction, or the loss in head due to friction. So your fluid could have a certain amount of energy at one end of a system, and it should conserve that energy and still have the same energy at the other end of the system. But what you'll find is actually as it travels through that system, it loses some of its energy due to friction, and that's translated into heat. So this is where we end up with what's called an energy loss. So the main issue in pipe flow problems is actually how to determine the energy loss, which is HF. And although HF or H sub F is referred to as energy loss in this equation, you'll often hear it referred to as head loss, or far more commonly in our industry, you'll hear it referred to as pressure loss. So the reason I've gone through all this is that if we actually think of the term pressure loss in terms of energy, it actually helps us to understand what pressure loss really means. Because it's something that confused me for quite a long time. People would say you've got a pressure drop or a pressure loss in the system. What does that actually mean? Well, it's actually meaning that the fluid is losing energy as it goes from it starts off getting energy input from the pumps, and it's got a lot of energy in there, pressure energy, kinetic energy, and some potential energy. And as it flows down the pipe and round the annulus, it loses all that energy until when it comes out at the surface, it has a bit of kinetic energy as it flows out, but it's actually not, it's got a lot less energy. And the reason where has all that energy gone? It's been dissipated as heat, frictional heat. So when people talk about pressure loss, they're really referring to a loss of energy in that fluid. And that really helped me to understand what pressure loss is meant. So there's a balance between the energy available and the energy that's lost through friction. And some of the earliest work performed in pipe friction was done by a chap called Osborne Reynolds, who you'll hear about again later. And he was a mathematician and an engineer, at the University of Manchester in the United Kingdom. Now basically Osborne Reynolds actually measured pressure losses in pipes of different diameters and lengths at different discharges, or basically different flow rates, and he had some pretty intriguing results. When he pumped at a low flow rate, the energy loss varied directly with the velocity of the fluid. Basically, if he doubled the flow, he ended up with double the pressure. And at high flow rates, the energy loss varied with the square of the velocity of the fluid. So if he doubled the flow at high flow rates, he ended up with 4 times the pressure. So he's kind of scratching his head and thinking, what's going on here? Well, what he ended up realizing was that there's 2 completely different flow regimes. Now, basically, he ended up setting up a further experiment, and it led to the distinction between what we actually now know as laminar flow and turbulent flow. There was a chap called Lord Kelvin at the University of Glasgow who introduced the term turbulence to describe the flow in a turbulent regime. Now, we'll actually look in more detail later at how we model flow, and we'll also discuss laminar flow and turbulent flow in more detail in another part of the module as well. But for now, what I wanted to draw your attention to was that if we can model flow, then we can predict pressure. Basically, if we can actually model the flow, we can predict the pressure. Osborne Reynolds could see that. Double the flow rate, double the pressure at a low flow rate. At a high flow rate, double the flow rate, and you end up with 4 times the pressure. So if we could model that, we could actually predict the pressure through any system that we have. And part of that flow modeling must actually involve predicting the flow regime, whether it's laminar or turbulent. So we'll talk about that later on, but for now, this is knowing whether it's laminar or turbulent or somewhere in between is actually crucial to being able to predict the pressure in a system. Now, we've mentioned the energy input into a system and the energy within the system. Now, what are the energy constraints on the system? Well, pressure energy is transmitted into the fluid by pumps. Okay, so you're basically causing the fluid to move by pumping it. Now, the pumps will only be able to pump at a maximum speed, and they will also only be able to hold a specific pressure before failure occurs. So there's only so much hydraulic horsepower that a pump has capacity-wise, and there is only so much pressure that its seals and its basic structure can actually hold back. So that is that's an energy constraint. And when we're doing flow modeling in our various software packages, the maximum pump pressure is a constraint on the amount of energy we can transfer into the fluid to make it flow. I'll be talking a bit about well plan later as well in another part of the module, but this is a graph from well plan. Now, basically, what we're saying here is that if the sum of the pressure losses in the system are greater than the maximum pump pressure, then we won't actually be able to pump the fluid. Now, this red line going across here with the shaded area above it is the maximum pump pressure. Now, we've got bit pressure loss, which is the pressure loss through the bit. We've got annular pressure loss, which is the pressure loss up the annulus. And we've got string pressure losses. If we add these 3 together, we get this blue line, which is your overall system pressure loss. We've got pressure up this axis and pump rate or flow rate along the bottom. So as you increase your pump rate, your pressure increases. And there will be a point at which you can no longer pump because your maximum pump pressure has been reached. So that's one constraint on the system. The other constraint on the system that I can think of right now is rock strength. If the sum of the pressure losses in the annulus, as you're pumping the fluid up the annulus, if the sum of the pressure losses in that annulus are greater than the rock strength, then the fluid will fracture the rock. So if we've got the annular pressure and equivalent mud weight here from a PWD tool, and we've got the fracture pressure of the rock, or basically we'll call it the rock strength, for want of a better term at the moment. If the pressure due to pumping that mud through the annulus is greater than the strength of the rock, then the rock will break and you'll start losing mud into the rock. So that's one other constraint. So these are energy constraints. There's only so much energy you can impart to that fluid using the pumps, and if you impart too much energy to the fluid in the annulus, then your rock will break down. So we're starting to build up a picture here of we're putting energy into the system, and it's lost as it travels right round the system. But as we'll see when we start talking about hole cleaning and such like, sometimes if it's lost too abruptly in one small area, then it'll overcome some of the constraints, and we can end up with pop-offs going on the pumps. We can end up with the rock fracturing, getting losses, etc. So now, just in conclusion, to wrap some of this up, you're now able to describe the basics of some of the basics of hydrodynamics, some more of the basic properties of a fluid, and we're also able to describe the difference between solid and fluid mechanics to a certain extent, and describe the role of energy in fluid flow, and we're able to consider some of the constraints on a system as well. And we can now move on to examine the flow models we actually use to describe fluid behavior, and also the methods we use to calculate the pressures within the system. And we'll actually, at some point, we'll be describing the system itself and all the components of that system.